Hi everyone. So in this bonus video, I'm going to go through separation of variables for the full time-dependent Schrodinger equation to show you where the time-independent Schrodinger equation comes from. And as I mentioned in the main class video, this is a really useful technique for solving partial differential equations that comes up really throughout all of physics and many engineering fields as well. Okay, so let's get started. Okay, so our goal today is to show that the time-dependent Schrodinger equation, which as a reminder looks like minus h bar squared over 2m partial squared psi, capital Psi, dx squared plus dx psi xt equals minus I equals IH bar partial psi xt dt. And what we want to do is show that this admits solutions of the form psi of xt equals psi of x e to the minus I e t over h bar, where lowercase psi of x satisfies the TISE minus h bar squared over 2m d squared psi of x dx squared plus v of x psi of x equals e psi. And again, as a reminder, we're assuming here that the potential energy, V of x, is time independent. Okay. So to start, so we assume that psi of xt can be written in the form some function of x. So I'll write that as lowercase psi of x plus some undetermined function of t f of t. This is why the technique is called separation of variables, because we're separating the full time-dependent space and time-dependent function into a piece that depends just on position and a piece that depends just on time. And you can see that what we're trying to show really does have this form. We're going to essentially be showing that our f of t is in fact this e to the minus I e t over h bar factor. Okay, so the first step here, right, so that's our first step. Our next step is going to be to plug that assumption into the time-dependent Schrodinger equation. So let's work out the derivatives we have to do. So the key thing is that if I d psi of xt d partial x, right, because we're assuming it has this form, the only part that depends on position is psi. So this I can write as the product f of t, which is a constant in regards to position, and then it's d psi of x dx, and I'm able to write this as a plain and not a d and not a partial derivative because psi only depends on x. In the same way, right, I can take another derivative of this, right, I can do d squared, or partial squared psi, capital Psi, partial x squared, playing the same game differentiating this with respect to x again gives me d squared lowercase psi dx squared. Now, in the same fashion, we can deal likewise with the time derivative. So partial capital psi, partial t. Now we pull out the spatial part. That ends up being psi of x d f, right here, df dt, and I'll write that argument, df of t dt. So if we now just plug and chug into our time-dependent Schrodinger equation, we get the following. Comes minus h bar squared over 2m. So we have this, so we have our f of t, we have our d squared lowercase psi dx squared, and then we have our v, we have our wave function, which is f of t, lowercase psi of x, or I should have written it the other way around, no big deal, and then my IH bar, and then I have my psi of x, d f of t dt. Okay, so the next step is to divide by, I'll slide this up just a little bit, divide both sides by the full wave function, so the product lowercase psi and f. So let's see what happens term by term here. So in the first term, if I divide by little psi f, I knock out this factor of f here, and I get a 1 over lowercase psi. So I have h bar squared over minus h bar squared over 2m, 1 over psi of x, d squared psi dx squared. Division by capital psi here knocks out everything except the v. So I have plus v of x. And then here on the right, I have I h bar, and then times 1 over f of t, df t, dt. So notice what we have here now. We've made a good bit of progress, because now notice that the right-hand side depends only on time, whereas the left-hand side depends only on position. Oops. So let's take a moment to sort of let that sink in. So, and I'll maybe see if I can, maybe I can do that. Yes, I can. In fact, hey, I'm figuring this out. I can roll the paper along, but you can still see the end of the last page. Okay, so here comes the trickiest part of the separation of variables argument, and it certainly took me a few, one or two times seeing this to convince myself that it actually works. So how this works is the following. So the key step, I'll label that 3. Key step, argue that both sides of the equation here equal a constant. Okay, so why is this the case? And, and by the way, let me call the constant E. E is just a constant now, but eventually we will we will argue that this, in 1 or 2 classes, that this E really should be associated with the energy of our system. So, okay, so I'll write that. So the key assumption is here. I'll write that up here. So I'll claim that this has to be a constant. Okay. Why? Okay. So notice that this side depends just on x. Okay? So LHS depends on x, right? This entire equation, right, this entire thing that we worked out just by manipulating the time-dependent Schrodinger equation, right, this is supposed, I'll just annotate this here, should hold for all x and t, right? So we said the left-hand side depends on x. If we pick a particular value of x, pick a value of x, right? If we pick a value of x and I evaluate the left-hand side, the left-hand side is going to be equal to some number, right? Because if I choose a value for x, suppose we pick x equals 0 for sake of argument, right? So LH side, left-hand side, is a number. What we have is then a number. That number is going to be equal to I h bar 1 over f df dt. This is now a first-order differential equation for f that you know how to solve. Here's the thing, right? If I pick a different value of x, right, and there's some non-trivial x dependence here, my number changes. Then whatever my solution f of t that I got from solving this equation is not going to work if this side equals some different number, right? And there's no way I can compensate for anything for it over on the right side here with anything that depends on x in any way, because we've explicitly constructed our lowercase f to only depend on time. There's nothing x-dependent over here. So if this number were to somehow change as x changed, we'd be up a creek. So the only way out is for the number to not change, i.e. this entire thing, 1 over psi, and I'll just d squared psi dx squared plus v equals constant. We can apply the same argument to the right-hand side. I won't write it in detail, but I'll just say it again. Again, this holds for all x and t. If I pick some value for t, right, now I have just an ordinary differential equation where I have x, some function of x and its derivatives equaling a number here. If, right, I now choose a different value of time, I get a different number, a different differential equation. Whatever psi worked over here won't work with a new number. So once again, the only way out is for this entire thing to be equal to a constant. And because these two things equal each other, well, they have to be equal to the same constant. So this means, so I'll now get rid of I'll write this last statement and then scooch the page up. Whoopsie daisy. That we have this, right, bar squared over 2m, 1 over psi of x, d squared psi dx squared plus vx equals our constant, which for now I'm calling e. And we also have IH bar, 1 over f of t, df of t, dt equals e. Okay, so let's analyze what we have here, right? If we multiply both sides of this equation by psi of x, aha, we end up with none other than the time-independent Schrodinger equation. H bar squared over minus h bar squared over 2m, our d squared psi dx plus our v psi equals our e psi. So here's our, this is the time independent Schrodinger equation. That's where it came from. So that part of the proof is done. We're again, as I said, we're going to subsequently be trying to find lowercase psi that satisfies this. But now let's turn to this part, the time-dependent part. Right? So if I multiply by f of t here, now I have IH bar df of t dt equals e times f of t. Okay, well, this is a first-order differential equation of the kind that you know how to solve by, also called separation of variables. Right, if you remember from like probably 225, I'm guessing, right? I want to get all the stuff with f on the one side, all the stuff, and then my dt on the other. And so actually I'm going to end up undoing what I just did, but I'll just divide by f here and then shove everything else to the right. So I get df of t divided by f of t equals, let's see, I have, I'll multiply by minus I instead of dividing by I because that's prettier. I get a minus I e over h bar dt. Okay, so you now know how to do this, so I just need to integrate both sides of this, right? So if I integrate, then and I'll just put in the initial condition as a constant of integration rather than picking doing definite picking limits and doing a definite integral. So if I integrate this, right, integral of df over f integrates to log, or natural log, f of t. This side equals minus I e t over h bar plus some constant of integration. So I'll just call that plus c. Okay. So now, right, you can simplify this by, right, you can just raise this entire thing to e to all of this to get rid of the log here. So so exponentiating okay, I get, so f of t equals e to, I'll just write this as x because I've got a lot to write here, i.e. capital Et over h bar plus c. I can factor out I can factor out e to the c here, right? Because when I have an e to the quantity a plus b is e to the a times e to the b. So I get, if I roll again over to here, or f of t, this gives me e to the c, and then now I'll go to writing this as e to the minus iet over h bar. Well, notice some things, right? So the constant of integration, as you probably know from diffie or some other math, is going to be related to the initial condition, right? Notice that at t equals 0, right, my f of t equals 0, the exponential goes to 1, equals e to the c times 1. So I can just go ahead and identify e to the c with that initial condition. And here's your, and you get your good old oscillating complex exponential here. Right? And so this is initial condition. So we're nearly done, right? So we can now just lump this all back together. Remember, so our assumption was that we assumed our capital psi of xt equals psi of x, f of t, or plugging in f here, right? That's my psi of x, my f of 0, t equals 0, e to the minus I e t over h bar. Now the last bit is to realize that this, right, this constant, you can just absorb into normalizing constant, the whatever factor has to appear in the wave function here in order for it to be properly normalized. Thing const of psi of x. And so, right, we finally reach the punchline. We in fact have capital psi of xt equals psi of x e to the minus I e t over h bar with psi of x satisfying our time independent Schrodinger equation, and we are done. Okay, hope this has been a fun little video. So again, this is a useful technique. So you might apply it in E and M to Laplace's equation for the electric potential. You can certainly apply it to the classical wave equation and prove the same kind of, get something quite similar. Other places that you can apply this to include the other classic PDEs, like the diffusion equation that governs how heat is transported through a body. Say also you can do this in various incarnations of the Navier-Stokes equations for fluid dynamics. So this is a really useful technique, and I'm glad you've had the chance to see it in this particular context. And now we've put our work with the time-independent Schrodinger equation on a firm ground.